Microsoft, and today I'll be co-presenting work with my colleagues Siva and Francis on how we can use data-driven methods to find bugs in configurations. So over the years, the PL community has made great advances towards more effective testing and verification for software. But today, increasingly, many services are built and operated primarily through configuration rather than code. So for example, configuration is used to control security policies, complex routing and computer networks, to tune performance for databases and servers, and much more. And just like with software, configurations are typically authored by humans, and humans are prone, as we know, to making errors. And the problem is that configuration bugs can be devastating. So for example, misconfigurations have regularly been the cause for widespread outages in major cloud infrastructure providers. And these outages can impact thousands of services and millions of users around the world. So let's take a look at a few examples of the types of misconfiguration that have had wide impact in the past. So here's one example of a misconfiguration where a network operator has used a /2 subnet instead of a /24 subnet in a firewall rule, which results in almost all traffic being dropped. In another example, an administrator has configured a timer for an IGP protocol that should not have been used at all, and this caused the device to take on too much traffic, leading to congestion. And here's another example from a radio unit where someone has configured the unit to use a 34 gigahertz frequency instead of a 3.4 gigahertz frequency on accident by including an extra 0 at the end. So a common theme across many of these configuration bugs is that they're very simple and quite obvious in hindsight. So the question that we have then is, given how simple many of these misconfigurations are, can we find configuration bugs simply by learning common configuration patterns from data? So in this data-driven approach, the key idea is to try to identify bugs as configuration anomalies based on the usage that deviates from the common case that we observe in other configurations. And to find such deviations, we need to look at a large corpus of example configurations. And fortunately, such configurations are typically readily available in real systems. So for example, you might have multiple configurations for different servers or for different network switches and so on. So we can use that information. Of course, finding bugs from examples alone while also having low false positive rate is challenging for a number of reasons. So for one, there's often many intentional differences between configurations. So for example, here is a network router configuration, and you can see that there's a static route used on each device, and the exact IP prefix used can differ, and that's intentional because it captures the unique local address space at the device. However, there's other differences that are absolutely not intentional and are bugs. So for example, there's this prepend command in this router, which is prepending string to a BGP protocol. And in the last configuration here, an operator has mistakenly used the value 2, thinking it means prepend twice instead of prepend the list of values. So that's one challenge. Another challenge is that many configurations employ ad hoc string formats to represent domain-specific constructs. And we need to extract information from these formats without prior knowledge about their structure or their meaning. And then finally, many configurations are written in standard data formats like JSON, XML, or YAML. And these make use of structured data like lists, nested lists, maps, and so on. And so in the rest of the talk, we'll mostly focus on the JSON format, but in the paper, we talk about how we can generalize this. So our paper introduces a tool called Diffy, and Diffy finds bugs in configurations using this data-driven approach. And it works in two stages. So in the first stage, we try to take in a collection of example configurations that are similar, and then we synthesize a template shown on the right here, which is just a representation of a set of configurations. And Diffy seeks to find a template that best generalizes the examples without overgeneralizing. So let's zoom in on this example template here, which I'm also showing in the JSON format. And we can see that for each JSON list, Diffy has determined the best description for the list, given the data it's observed. So for example, this actions list is annotated as having order matter. So in other words, you don't want to deny or accept a route before doing the prepend action. And in another list, for example, the static routes, it's annotated as being unordered, so the order doesn't matter. And in another case, this length match filter component is best summarized with a repeat template, which states that every element of each list in each configuration matches one of the given sub-templates that it's learned. And then for each JSON string here, Diffy has synthesized a template that best captures and generalizes the concrete examples it observed in the example data that we gave it. And the parts of the configuration that vary are left as these template holes, for example, some substring that might differ from config to config. So that's the first stage. And then in the second stage, we use unsupervised anomaly detection to identify likely bugs and report these to the user, along with a score of how likely the bug is. So as an example from this actions list, we can see that if we have the distribution of values that were observed for this prepend statement. And in 43 of the configurations we had, the value was 65,000, which is significant in this particular protocol. In 2 of the configurations, the value was 65,001. And in 3 of the configurations, the value was 2. And so it'll actually flag 2 as the likely bug because it's both less common and further away from typical values. And just as another example, here there's an optional second static route in some of the configurations, 3 of them. And the third octet of the prefix differs between these configurations. However, when we analyze the distribution, we see that it's rather uniform, which indicates that it's likely an intentional difference. So now let me hand it off to my colleague Siva, who's going to talk about how Diffy actually comes up with this template in the first place.
Thank you, Ryan. And let's jump in. So the basic building block of Diffy is a fast string template synthesis algorithm that is used for extracting commonalities and differences across configs for downstream anomaly detection. Consider a very simple case of MySQL database configurations. There is a parameter called max heap table size that is configured to have a particular memory size. Given these values, we want to compute a string template that best describes these string values. A template is just a representation of a set of strings. One way to represent these strings is with the any token, which we use to match all strings. However, the token any is too broad because it captures all other strings as well. Alternatively, this next template, which is a disjunction of 3 exact strings, it is very precise, but is complex and likely overfits the examples. In this case, a compromise such as a number followed by any strikes a balance between conciseness and specificity, which is the goal of our synthesis. We provide Diffy with a set of tokens like number and any from the previous slide defined using regular expressions. By default, to Diffy, we provide tokens for objects like numbers, floating points, hex values, and more. The users can also provide custom regular expressions to express domain-specific concepts such as for a file path or an IP address. But we also need the string template synthesis algorithm to be fast as we process millions of lines of config, and string template synthesis is repeatedly used as a subroutine for synthesizing higher order structures like lists and objects. Let's take the same memory unit example from before along with these 2 tokens. We also assume a cost for each regex token between 0 and 1 for every character of a string matched by it. Cost 0 means a perfect match and a cost 1 means a worst match. It turns out that we can find the optimal pattern that combines these 2 values 15M and 10M using a dynamic programming algorithm. If we lay out the characters of the strings in a 2D table, the idea is to find the lowest cost path from the top left to the bottom right by filling out this table. As you are all aware, this dynamic algorithm is related to the idea of string edit distance, but we instead try to find the minimal regular expression aware edit distance between strings. Now let's start filling the table. You can match the first character in one of the 2 strings, but not in the other with an any token, and the cost is 1 as we match just 1 character. Similarly, we can fill out the first row and first column with the cost as we can only match with an any token. For the next cell, we notice that both the strings have the same exact character and therefore can match without any additional cost, which is cheaper than matching with any token either from left or from top. Now this is where it gets more interesting. as we try to match the first two characters, which are the 1 and 0, with the first character 1 in the 15M string. In the traditional string edit distance algorithm, you match with any for the left side for the character 0 with a cost of 1. However, using the number token, we can make a backwards jump to the first cell as the number token matches 1 and also 1, 0. Since the token is matching 3 characters, we get a cost of 0.2 into 3, which is 0.6. For a given cell like this, we consider all possible backward jumps for each regular expression token we have and find the lowest possible cost. We continue filling the dynamic programming table using the number token, as it still matches the prefixes of both strings. Next, when we encounter the character M from only one string, we match it with any token. And finally, since both the strings end with character M, we have an exact match and update the cost from a diagonal cell. Now, we can retrace the table from the bottom right corner to the top left corner and identify the lowest cost case at each step. We can retrieve the lowest cost pattern, which in this case is 1 followed by a number token followed by M. So going back to our original example, so now what do we do if we now want to template find the best pattern of 3 or more strings? We can just repeatedly find the best pattern by folding in a new string. So how does it happen? Here I am showing the next dynamic programming table that we construct for the new string 200 at the top and the previous pattern we learned 1 num M on the left. This time the best pattern is shown along the highlighted squares. The number token matches both the entire string 200 and the 1 num on the left, since a 1 followed by a number is still a number, and we determine this using a regular language inclusion check. Lastly, the any token matches the final character M without consuming any characters from 200. So now the final template of these 3 strings is num followed by any. This is exactly what one might hope for, since it lets us capture both the values of the memory size as well as the optional units. There are many more details and challenges that we discuss in the paper, but which I will not have time to cover in this talk. For example, each backwards jump from the dynamic programming algorithm involves a language inclusion check. Doing so naively is expensive. In the paper, we show how we can find all matching substrings efficiently in a single pass using an automaton construction. Similarly, we also show how to synthesize templates for higher ordered structures like list with the string templates as a subroutine using classical algorithms such as sequence alignment, minimum cost matching, and hierarchical clustering. Now that we have template, we apply unsupervised machine learning to find likely bugs in the values captured by the template. We use a technique called isolation forest, which can find outliers in a data set. For example, if we look at the parameters of the num token, in the pattern, we have this list. The algorithm returns the following scores for these values, and we can see that 2 has a high anomaly score. Even though 65001 has lower frequency than 2, it does not stand out, as isolation forest is based on the observation that anomalies are both few and different. That is, they not only have infrequent occurrences, but also consist of values that noticeably differ from the normal, making them easier to separate from other samples. From the earlier static out example that Ryan showed, we see that all the 3 values from the digit in the 3rd octet of the prefix are close and have the same frequency, so none of them have a high score. Finally, let's look at how Diffy performed in practice. We use Diffy on 3 data sets to demonstrate Diffy's versatility, scalability, and accuracy. We used configurations from Microsoft's wide area network consisting of thousands of routers and close to 10 million lines of configuration. Next, we obtained 42 configurations for radar units of an operational 5G test bed. Finally, we evaluated a set of MySQL configurations, which was the target of prior work. So how well does Diffy do on these data sets? Even on the largest data set, which is the wide area network we have, Diffy finishes within 20 minutes, even when processing millions of lines of config. This is actually about 2 orders of magnitude faster than if we used existing string template synthesizers, such as Flash Profile from OOPSLA 2018. On all the 3 data sets, we found that Diffy achieves high precision and recall. On MySQL, Diffy identified 74% of the issues flagged by prior tools that were specialized to that domain, while generating far fewer false positives. For each data set, Diffy found numerous issues, of which I will discuss just a few. First, Diffy learned a disjunction of two templates for the overload keyword in the IS protocol. The use of a 1200-second timer is uncommon and had previously caused a major outage for Microsoft. The configuration issue was resolved, but automation later mistakenly reapplied the flawed setting. Diffy detected this misconfiguration as a high confidence anomaly from the template shown on the slide, and we were able to alert the operators in time. In another instance, Diffy discovered inconsistencies in regular expression used for filtering. Some routers configured a regular expression with a caret symbol, while most did not. Diffy found that the value of the first any token was typically an empty string and only really the caret symbol. When present, this caret symbol requires that you erroneously require a match at the beginning of the BGP protocol community string. For the RAN, Diffy found 62 true positives. An example bug in the RAN is the case where Diffy successfully identified the misconfigured frequency with a synthesized template, 3 followed by a number, and the value of the number being different and outside the range of typical values, which all fall into the N78 band. In another case, Diffy flagged an incorrect field for the attenuation, which controls the transmit power. For MySQL, Diffy identified fields with patterns like num followed by any, like the example we saw earlier, where number captures the value and any captures units. If users used invalid inputs like KB, Diffy detected these cases due to their rarity. In another instance, there was a type error where a file path was expected, but the user provided off. Prior work used built-in domain knowledge, recognizing off as a Boolean value and flagging it as a type error. Diffy also found the same issue since it learned the template path or off, with the latter occurring once and the former every other time. With that, I conclude. Thank you, and we are happy to take questions.
Thanks to the previous talk where we saved some time, we have enough time for a few questions. Please.
Hi, thanks for the talk. Really impressive results. I was wondering about the core sort of template synthesis algorithm that uses regular expression synthesis. So you had a procedure there with the dynamic programming, and it seemed like you were assuming the regular expression maybe is decomposed into n parts or something like that. I guess the question is, what specific subset of regular expressions do you support in that algorithm? Is it like, does it work for any regular expression, or?
It works for any regular expressions, and we consider, so number here is 0 to 9 plus. So you can have other ones like the ones that I showed, floats, hexadecimals, and alphanumeric. There can be any other kind of regular expression tokens.
But not just the subset that you consider, but any arbitrary regular expression.
That's where we show that the user can provide like IP address or path. They can provide any other regular expression that they think are suitable for their domain.
Okay.
Just to add a little more flavor. So if the regular expression is easily extended, so like if a number, adding another digit, it remains a number, then we can optimize the implementation, because now you can kind of greedily take the longest match in the dynamic programming table. So for some regular expressions, you can actually optimize the implementation as well.
Got it. Thank you.
I'll follow up with the previous question. So if you
Can you come near the mic, please?
If you generalize the first part of the problem, like you're trying to synthesize the templates, right? So is it like something like generalizing a grammar of the configurations? Like if you consider the problem like this, have you tried some classical algorithms like L star that generalizes from examples? So have you given a thought about that?
Yeah, that's a good question. I think that is the right way to think about the problem. We considered some of those algorithms early on. I think we were concerned about scale, which is what led us to this, dynamic programming algorithm. But yeah, I think that could also be a valid approach. We could look into. Yeah.
Okay, I also have two questions regarding the regular expression synthesis. The first one is, are you manually selecting the weights for each one of the productions?
Yes, we are.
Okay.
The intuition behind different weights is that the regular expressions which are specific and capture fewer strings are supposed to be given better choice. For example, if you have an alphanumeric and number token captures fewer strings than alphanumeric, and we want number to be prioritized if the string is all digits. So that's the intuition, and based on that, you can give the weights for the tokens that you have in the input set.
Okay, thank you. And my second question is, when you go from the pairwise case of generating a regular expression from 2 concrete strings, you generalize this for 3 strings by doing the dynamic programming algorithm on the regular expression and a new string. Is this approach invariant to permutations of the input strings? Like, if you have reverse the order in which you do this unification pairwise, is it going to give you the same regular expression?
Yeah, that's a great question, great observation. It is not. So the order does actually matter. And in the implementation, we actually experimented with basically, pre-sorting the strings based on similarity. And sometimes that can actually give you a better template. For performance reasons, we also we do a greedy clustering. We didn't show it, but we learn a disjunction of patterns of templates. So we do a greedy clustering based on which has the lowest next cost, which group you can put the current string with. So that also can influence the final templates you get. But one other thing I'll note is a lot of times what we found is actually the exact template doesn't matter. So even if it's not exactly what you would expect a human to write, for the purpose of the anomaly detection, even if you get it slightly wrong, you'll still find the bug in some part of the template a lot of the times, right?
Yeah, makes sense. So thank you. Great work.
All right, let's thank the speakers.